This is Lecture 4, Introduction to Bivariate Regression. By the end of this lecture, you should be able to understand the intuition behind bivariate regression, calculate the coefficient and constant for a bivariate regression, conduct a significance test on a regression coefficient and constant, and interpret the results of an ordinary least squares regression. In the previous lectures, we discussed how we use statistics to determine if there's a statistical relationship between an independent and a dependent variable. Bivariate regression is one way in which we can determine the statistical relationship between two variables. It is called bivariate regression because there are only two variables in the regression, one independent variable and one dependent variable, hence bivariate. In order to demonstrate the intuition behind a bivariate regression, I'm going to use the following hypothesis as an example. As GDP per capita increases, net migration increases. In this example, GDP per capita is the independent variable and net migration is the dependent variable. Changes in GDP per capita influence changes in net migration. To understand the intuition behind bivariate regression, imagine we plotted our independent variable and dependent variables on a graph. We placed our independent variable on the x-axis, GDP per capita here, and our dependent variable on the y-axis, net migration here. Then we plotted the values for each observation on this graph. All of these dots here represent the individual observations. Next, imagine we drew a line straight through the middle of all of these points. Then we calculated the equation for that line. If you remember from your algebra classes, the equation for a line is y equals the slope times t If you remember from your algebra classes, the equation for a line is y equals the slope times x plus the y-intercept. Remember, the slope tells you the steepness of, I guess I should do this two times. If you remember from your algebra classes, the equation for a line is y equals the slope times x plus the y-intercept. Remember, the slope tells you the steepness of a line, or in other words, it tells you by how much y changes when x changes. The y-intercept tells you the value of y when x equals 0 and the line passes through the y-axis. You will calculate a similar equation for a bivariate regression. However, we will make a few modifications. First, we will refer to our y as the dependent variable. We will refer to b, the slope, as the coefficient. We will refer to x as our independent variable. We will refer to a, the y-intercept, as our constant. And we will include an error term in our models. The error just tells us how far individual observations here deviate from this line. We will talk more about the error term after exam 2. There is one final modification we make to the equation for a line in bivariate regression. We will place hats over y, b, a, and e. We cannot tell from a sample what the true y, b, a, and e are. Instead, we make an estimate of what they are based on our sample. Now on to calculating b hat and a hat. These are the equations for calculating the coefficient b hat and the constant a hat. In the next few slides, I will walk you through the steps of calculating the estimated coefficient b hat. However, I will briefly go through the equation here. In the numerator here, you are determining if, for each observation, the independent variable xi is deviating from the mean of the independent variable x bar in a similar/different direction and magnitude as the dependent variable yi is deviating from the mean of the dependent variable y bar. Although this calculation is a little different, this is very similar to the Pearson's correlation coefficient R. We're determining if the independent variable is deviating from its mean in a similar/different direction and magnitude as the dependent variable is. Now I'm going to walk you through the steps of calculating a bivariate regression. I strongly encourage you to have the b hat and a hat equations written on a paper next to you so that as I go through the steps it will make more sense. I will use the example from the beginning of the lecture in this demonstration. Recall that the hypothesis was, as GDP per capita increases, net migration increases. In this example, GDP per capita is the independent variable and net migration is the dependent variable. I gathered data on GDP per capita and net migration for 178 countries in the world in 2010. I'm going to calculate a bivariate regression for this data, but I'm only going to show you the first 4 observations in the slide because I can't put all of the observations on the slide. The first step in calculating a bivariate regression is calculating b hat. I showed you the calculation 2 slides ago. Now I'm going to take you through the steps in calculating the equation. I will start with b hat. The first step in calculating b hat is calculating the mean of the independent variable x and the mean of the dependent variable y. You have to remember that the independent variable is x and the dependent variable is y, otherwise you will miscalculate your answers later on. So using the data from all 178 observations, I calculated the mean of the independent variable, GDP per capita, and it was 9902.18. And I calculated the mean of the dependent variable, net migration, and it was 5832.34. The second step in finding b hat is subtracting the mean of the independent variable x from each individual x observation. In this case, this means you have to subtract the mean of GDP per capita, 9902.18, from the values of GDP per capita for each observation. So here we have a value of 340.93 for GDP per capita for observation 1. So I calculate 340.93 minus 9902.18, and the answer is negative 9561.25. So here we have a value of 3288.43 for GDP per capita for observation 2. So I calculate 3288.43 minus 9902.18, and the answer is negative 6613.75. You would continue doing this for each observation. The third step in finding b hat is subtracting the mean of the dependent variable y from each individual y observation. In this case, this means you have to subtract the mean of net migration, 5832.34, from the values of net migration for each observation. So here we have a value of negative 381,030 for net migration for observation 1. So I calculate negative 381,030 minus 5832.34, and the answer is negative 386,862. And here we have a value of negative 47,899 for net migration for observation 2. So I calculate negative 47,899 minus 5832.34, and the answer is negative 53721.3. We would continue doing this for each observation. The next step in calculating b hat is multiplying the corresponding values from steps 2 and 3. So in observation 1, the value of xi minus x bar was negative 9561.25, and the value of yi minus y bar was negative 386,862. So negative 9561.25 times negative 386,862 is 369,888.7548. And in observation 2, the value of xi minus x bar was negative 6613.75, and the value of yi minus y bar was negative 53721.3. So, negative 6613.75 times negative 53721.3 is 355,299,512.4. We would continue doing this for each observation. The next step in calculating b hat is adding all of the values from step 4 together. After adding all of the 178 values together, the value I calculated was 707,219,474,786.07. Note that this value is the numerator in the b hat equation. The next step is squaring the values from step 2. Recall that in step 2, we subtracted the mean of x from each individual x observation. Here, we simply square those values. So, for observation 1, xi minus x bar was negative 9561.25. Negative 9561.25 squared is 91417,501.56. And for observation 2, xi minus x bar was negative 6613.75. Negative 6613.75 squared is 43741,689.06. The next step in finding b hat is adding all the values from step 6 together. After adding all of the 178 values together, the value I calculated was 37,134,641,665.36. Note that this value is the denominator in the b hat equation. The last step in calculating b hat is dividing the values from step 5, the numerator, by the values from step 7, the denominator. 707,219,474,786.07 divided by 37,134,641,665.36 is 19.04. So our slope or coefficient b hat is 19.04. Next, we have to find a hat. A hat is a much easier calculation. A hat equals the mean of y minus b hat times the mean of x. Remember that I calculated these values earlier in the lecture slides. The mean of y is 5832.34, b hat is 19.04, and the mean of x is 9902.18. 5832.34 minus 19.04 times 9902.18 equals 5832.34 minus 188,537.51, which equals negative 182,705.17. So, using our estimates for b hat and a hat, our regression equation is net migration hat equals 19.04 times GDP per capita minus 182,705.17. Note that although we add a hat up here, we are subtracting the number here because the a hat was negative. Now, after you calculate your regression equation, you can check to see if you did the math correctly. If we input the mean of x, or the mean of the independent variable, into the regression equation we calculated, the equation should equal the mean of y, or the mean of the dependent variable. The mean of x was 9902.18, and the mean of y was 5832.34. The equation was y hat equals 19.04 times x minus 182,705.17. So placing the mean of x, 9902.18, here, we have 19.04 times 9902.18 minus 182,705.17, which equals 5832.34. 5832.34 is the mean of y. So why does the equation produce the mean of y when we input the mean of x into it? Because the regression line that we calculated goes through the point mean of x, mean of y. Remember from earlier in the lecture I told you that regression takes into account if one variable varies from its mean in a similar / different direction and magnitude as the other variable. So it is not surprising that the regression line goes through the mean of x and y. Now recall from the beginning of the lecture, I told you that we use bivariate regression to determine if there's a statistical relationship between two variables. So how do we determine this relationship from the regression? The regression coefficient b hat tells us the impact that the independent variable has on the dependent variable. If the coefficient b hat is 0, that means that the independent variable has no impact on the dependent variable. A slope of 0 means that as x changes, y does not change. Or in other words, as the independent variable changes, the dependent variable does not change at all. However, based on our hypothesis, we do not think the coefficient is 0. Instead, we expect it to either be greater than 0 or positive, or less than 0 or negative. If the coefficient is positive, then we say that as the independent variable increases, the dependent variable increases. Note that if this was the case, the coefficient or slope, or b hat, would be positive. That is why we say this would be a positive relationship. If the coefficient is negative, then we say that as the independent variable increases, the dependent variable decreases. Note that if this is the case, the coefficient or slope would be negative. That is why we say this would be a negative relationship. So in order to figure out whether the coefficient is different from 0, we conduct a t-test. The first part of the t-test is writing the null hypothesis. In this hypothesis, we expect that the independent variable has no effect on the dependent variable. As the independent variable changes, the dependent variable stays the same. A more sophisticated way to write this is h subscript 0 colon b hat equals 0. The h indicates that you have a hypothesis. The 0 means that it is the null hypothesis. B hat is your coefficient. Stating this in other words, you have the null hypothesis is that the coefficient is equal to 0. Next, you have to write your alternative hypothesis. You choose your alternative hypothesis based on your theory. If you expect that your independent variable has a positive impact on your dependent variable, your alternative hypothesis should be, as the independent variable increases, the dependent variable increases. The more sophisticated way to write this hypothesis is h subscript 1 colon b hat is greater than 0. The h indicates that you have a hypothesis. The 1 means that it is the alternative hypothesis. B hat is your coefficient. Stating this in words, we have the alternative hypothesis is that the coefficient is greater than 0. If, on the other hand, you expect that your independent variable has a negative impact on your dependent variable, your alternative hypothesis should be, as the independent variable increases, the dependent variable decreases. The more sophisticated way to write this hypothesis is h subscript 1 colon b hat is less than 0. The h indicates that you have a hypothesis. The 1 means that you have an alternative hypothesis. B hat is your coefficient. Stating this in words, we have the alternative hypothesis is that the coefficient is less than 0. After you write your null and alternative hypotheses, you conduct a significance test or t-test to determine if your b hat is different from 0. You turn your b hat into a t-score to determine if it is statistically different from 0. Now, you learned about t-scores in depth in your other statistics classes, so I'm not going to go into too much depth about the fundamentals of t-scores. I will simply provide a brief overview. You calculate a t-score when you transfer a value onto one of several t distributions. T-distributions have a mean of 0. They are also bell-shaped and symmetrical, but are not normally distributed. Instead, their variance depends on the sample size. This image shows you how a t-distribution takes into account sample size. Here is a z-distribution in blue, which is normally distributed and has thousands of observations. As you can see, there is little variance in this distribution as observations are close to the mean. But as you can see with the t-distributions, there's a lot more variance as the number of observations decreases. As the number of observations decreases from 30 purple to less than 30 pink, the t-distribution gets flatter. Now, how can a t-score and the t-distributions help us determine whether our coefficient b hat is close to 0 or far from 0? Very briefly, most t-scores fall close to 0. All of these t-scores here are very close to 0. As you can see, 0 is the most common t-score here, as the peak of the histogram tells us there are a lot of observations here. Once the t-score gets somewhere between 1.6 standard units above or below the mean of 0, about here, that is unusual. There aren't many t-scores this big. Only about 5% of the t-scores fall beyond this point or this point. When we turn our b hat into a t-score, we can tell if that t-score is close to 0 in the t-distribution, meaning we can't tell if the independent variable has an effect on the dependent variable, or far away from 0 in the t-distribution, meaning the independent variable has an effect on the dependent variable. When we expect a positive relationship between our independent and dependent variables, we expect our t-scores to be positively different from 0. When we expect a negative relationship between our independent and dependent variables, we expect our t-scores to be negatively different from 0. Now, these two curves that I just showed you are the same. However, as I told you in this slide, there are several different t-distributions depending on the number of observations you have. As the number of observations decreases, the t-distribution gets flatter. The result of that is that it will make it harder for you to find results that are statistically significant. As it gets flatter, it is harder to calculate a t-score that is positively different from 0 up here and negatively different from 0 down here. Intuitively, that makes sense because when you have fewer observations, you have less information, so it should be harder for you to find statistically significant results. Okay, now I'm going to show you how to conduct a significance test or t-test for your b hat. To demonstrate how to do this, I'm going to conduct a significance test on the b hat from our equation earlier in the lecture. Recall from the beginning of the lecture I had the following hypothesis: as GDP per capita increases, net migration increases. Based on this hypothesis, I expect there to be a positive relationship between my independent variable GDP per capita and my dependent variable net migration. My regression equation with net migration and GDP per capita produced a b hat of 19.04. So the first step in determining whether this b hat is significant is writing the null hypothesis and the alternative hypothesis. The null hypothesis is h subscript 0 colon b hat equals 0, and the alternative hypothesis is h subscript 1 colon b hat is greater than 0. I chose greater than 0 because I expect there to be a positive relationship between GDP per capita and net migration. The step in determining whether b hat is significant is choosing our decision rule template. We choose our decision rule template based on our alternative hypothesis. If we expect a positive relationship between our independent and dependent variables, we choose the following decision rule. If the t-statistic I calculate is greater than the positive t-value from table 6.4, I can reject the null hypothesis. I can conclude that the coefficient is greater than 0. Otherwise, I cannot reject a null hypothesis. I cannot conclude whether the coefficient is different from 0. If we expect a negative relationship between our independent and dependent variables, we choose the following decision rule. If the t-statistic I calculate is less than the negative t-value from table 6.4, I reject the null hypothesis. I can conclude that the coefficient is less than 0. Otherwise, I cannot reject the null hypothesis. I cannot conclude whether the coefficient is different from 0. Note that we will be working with two t-values in significance tests, one from table 6.4 and the one you will calculate yourself. This is important to remember so you don't get confused. Also note that the values from table 6.4 are all positive. When we use this negative t-value template here, we have to put a negative sign in front of the t-value. So recall that based on my alternative hypothesis, I expect there to be a positive relationship between my independent variable, GDP per capita, and my dependent variable, net migration. Hence, I should choose the following decision rule. If the t-statistic I calculate is greater than the positive t-value from table 6.4, I can reject the null hypothesis. I can conclude that the coefficient is greater than 0. Otherwise, I cannot reject the null hypothesis. I cannot conclude whether the coefficient is different than 0. Next, you have to choose the t-value you will use from table 6.4 on page 146 in your textbook. You will choose a row and a column in this table, and the t-value that intersects that row and column will be the t-value you use. In order to choose your row, you have to calculate the number of degrees of freedom you have. The number of degrees of freedom equals the number of observations n minus the number of independent variables p minus 1. Recall that I had 178 observations in my analysis, and I had one independent variable. So 178 minus 1 is 176. So I look in the table under the degrees of freedom column for the 176th row. If the number is not listed, I choose the next lowest number. Hence, I choose row 120. Next, you choose a significance column. When conducting a significance test for coefficients in this class, always use the 0.05 column. Recall that we are determining whether our t-score is greater than 0 or within 5% of t-scores that are very far above the t-value of 0 in the t-distribution. 0.05 and 5% are synonymous. When I look at the t-table and look for the t-score that intersects the 120 row and the 0.05 column, the t-value turns out to be 1.658. So I insert this value into my decision rule template. If the t-statistic I calculate is greater than 1.658, I can reject the null hypothesis. I can conclude that the coefficient is greater than 0. Otherwise, I cannot reject the null hypothesis. I cannot conclude whether the coefficient is different from 0. Step 4 in determining whether your b-hat is different from 0 is actually turning your b-hat into a t-score. The calculation is t equals b-hat minus 0 and that value divided by the standard error of b. I already showed you how to calculate b-hat. I don't expect you to calculate the standard error of b-hat. I will always give this number to you. However, I will tell you the intuition behind the standard error in the t-test. The standard error tells us how well the independent variable predicts changes in the dependent variable. If the independent variable predicts changes in the dependent variable very well, there is not a lot of error, e-hat. The error is just the actual values of the dependent variable y minus the predicted values of the dependent variable from the regression equation we produced, y-hat. Note that the error is in the numerator of the standard error of b-hat. So the smaller the error, the smaller the standard error is. Now note that the standard error is in the denominator of the t-score calculation. The smaller the standard error is, the smaller the denominator is. The smaller the denominator is, the larger this t-score should be. This means we are more likely to get significant results, as the t-score should be large and different from 0. In sum, when our independent variable predicts our dependent variable well, then our errors are smaller, our standard error is smaller, our t-score is larger, and we get significant results. Alternatively, when our independent variable does not predict our dependent variable well, our errors are larger, our standard error is larger, our t-score is smaller, and we do not get significant results. So now we are going to calculate our t-score. Remember that the b hat from our equation was 19.04. I calculated the standard error for b hat. It was 3.39. So 19.04 minus 0, and that value divided by 3.39 is 5.62. Now we compare the t-score we calculated to the t-score from our decision rule template. Remember that our decision rule was, if the t-statistic I calculate is greater than positive 1.658, I can reject the null hypothesis. I can conclude that the coefficient is greater than 0. Otherwise, I cannot reject the null hypothesis. I cannot conclude whether the coefficient is different from 0. The t-value we calculated was 5.62. 5.62 is greater than 1.658. Hence, we can say our coefficient b hat is greater than 0. The conclusion we make is the t-value is greater than 1.658, so I can reject the null hypothesis. I can conclude that the coefficient is positive and statistically significant at the 0.05 level. Note that we can also add, I can conclude that as GDP per capita increases, net migration increases. Note that if we were working with negative values, as in you expected the coefficient to be less than 0, and we got significant results, you would say that the coefficient is negative and statistically significant at the 0.05 level. You could also add, as the independent variable increases, the dependent variable decreases. Also note that if in the test we just ran, if the score we calculated was not greater than 1.658, then we would have said that we cannot reject the null hypothesis. The coefficient is not significantly different from 0. We would not be able to make any conclusions about the relationship between the independent and dependent variables. Now I'm going to show you the significance test for a hat, the constant. It is similar to the significance test for b hat. We want to know if a hat is different from 0, except we don't have any expectation that a hat is positively different from 0 or negatively different from 0. So we run what is called a two-tailed test. Recall that in the t-distribution, most t-scores fall within or very close to 0. We are going to transform our a hat into a t-score and determine if the t-score is much higher than 0 or much lower than 0. In this case, we are going to determine if our t-score is within 2.5% of t-scores above 0 or within 2.5% of t-scores below 0. So we're going to conduct a t-test where we look for t-values that are either positively different from 0 or negatively different from 0. The decision rule template for this t-test is, if the t I calculate is greater than my positive t-value from table 6.4, the constant is greater than 0. If the t I calculate is less than my negative t-value from table 6.4, the constant is less than 0. Otherwise, I do not know if it is different from 0. Now we need to find the t-value from table 6.4. This is similar to what we did before. We look for the t-score that intersects our degrees of freedom row and our significance column. Our degrees of freedom, df, are the number of observations n minus the number of independent variables p minus 1. Recall that I had 178 observations in my earlier analysis. and I had one independent variable. So 178 minus 1 is 176. So I look at the table under the degrees of freedom column for the 176th row. If the number is not listed, I choose the next lowest number. Hence, we choose row 120. Next, we find our significance column. We will always use the 0.025 column for significance test for constant in this class. We want 5% significance, so we look at 0.025 or 2.5% in both tails. 0.025 and 0.025 is 0.05 in total. Since our degrees of freedom row was 120, and our significance column was 0.025, the t-score we will use is 1.980. Inserting this t-score into our decision rule template, we have, if the t I calculate is greater than 1.980, the constant is greater than 0. If the t I calculate is less than negative 1.980, the constant is less than 0. Otherwise, I do not know if it is different from 0. Next, we calculate our t-score. The t-score calculation for a hat is similar to the t-score calculation for our b hat. T equals a hat minus 0, and that value divided by the standard error of a hat. I will not expect you to calculate the standard error of a hat. I will give that value to you. I just wanted to show you the calculation for it. As you can see, it takes into account how well the independent variable predicts the dependent variable, as it includes the error term in its calculation. So applying this to our example, our a hat was negative 182,705.17, and the standard error of a was 59285.2. So negative 182,705.17 minus 0, and that value divided by 59285.2 is negative 3.09. So our t-score was negative 3.09. Recall that our decision rule was, if the t I calculate is greater than 1.980, the constant is greater than 0. If the t I calculate is less than negative 1.980, the constant is less than 0. Otherwise, I do not know if it is different from 0. T equals negative 3.09, so the t is less than negative 3.09, so the constant is less than 0 and significant at the 0.05 level. Note, if t was greater than 1.980, then you would say the constant is greater than 0 and significant at the 0.05 level. Also note, if t was not greater than 1.980 or not less than negative 1.980, you would say the constant is not significantly different from 0.